So let's hear it. A big thank you for Kevin and David. So thank you for a fascinating week, and thank you for inviting me. I'm delighted to be here. So I would like in this talk to tell you about a conjecture and what the evidence is for the conjecture. So throughout the talk, G will be a reductive p-adic group, and I want it to be connected and split. And in this context, you're working over a p-adic field F. What connected means that G of F bar, you go to the... This should be connected in its Zariski topology. It's an affine variety over F bar. It should be connected in its... in other words, you can't decompose it into disjoint varieties. That's what connected means. And split. Split means that the maximal p-adic torus in there has the right dimension, has the dimension it should have. Now, we have the usual suspects up there, these classical groups. These are examples of groups which are connected and split. And then the smooth dual, that's the set of irreducible smooth representations. The representations are in vector spaces over the complex numbers. The smooth dual will be denoted by G with a hat over it. G with a hat over it. Like that. I was giving a talk about this in Warsaw a while back, and one mathematician didn't like my hat. He said it was too small and that I wasn't using tech correctly. This was in the middle of the talk. He actually brought this up. Okay, so I took that to heart, and I hope you will like my hat. All right, now within, I will explain this. Within the smooth dual, there are subsets known as the Bernstein components, and the smooth dual, in a canonical way, the smooth dual is the disjoint union of the Bernstein components. So I want to explain a conjecture due to my co-workers, Aubert, Pleiman, and Soloveld, and which says that each Bernstein component is an affine variety over the complex numbers. And these affine varieties are explicitly identified as certain extended quotients. Now, all of this is heavily dependent on the theory of Bernstein, of Joseph Bernstein. And I will try to explain some of the basic points in the beautiful theory of Bernstein. It's called the theory of the Bernstein center. All right, so everything I will try to say today is joint work with my co-workers, Anne-Marie Aubert, Roger Pleiman, and Martin Soloveld. Here is a reference. This is an expository paper, and it will give other references to other papers that my co-workers and I have published. But this is an expository paper. Perhaps you would find it interesting. All right, so it's well known that there's an equivalence of categories between algebras over the complex numbers, which are commutative, unital, has a unit, a 1, finitely generated as an algebra, and nilpotent free. It has no nilpotent elements except 0. And on the other hand, we have affine algebraic varieties over C. The equivalence of categories is given by mapping an affine variety X to its coordinate algebra, O of X, the algebra of complex valued algebraic functions on the variety. Well, you have to put a little op there. That means opposite category, because this reverses the direction of morphisms. If you have a morphism of algebraic varieties from X to Y, you get a map of algebras, of coordinate algebras in the opposite direction. So you put a little op up there. Now, suppose we have not just an affine variety over the complex numbers, but suppose we have also a finite group acting as automorphisms of the affine variety. Then we can form the quotient variety that you just collapse each orbit to a point, And this will again be an affine variety. And that's the quotient. This will be referred to as the quotient or the usual quotient, something like that. But now we're going to do something a little bit different, quotient in a slightly different sense. So for each point, that means each C rational point in the variety, we let gamma sub x will be the stabilizer group. That is the subgroup consisting of all elements in the finite group gamma which fix little x. And then we take the set of conjugacy classes. And now the extended quotient is obtained by replacing the orbit of x by the set of, instead of just collapsing the orbit to a point, we shall replace the orbit by this set of conjugacy classes of the isotropy group. Now, I would like to make a very elementary remark. This is a very elementary remark, but perhaps it's worth making. If we have the, if this is our affine variety, we have a finite group gamma acting on it as automorphisms of the affine variety. If we take an orbit, suppose we have 2 points in the orbit. We have an orbit, we have 2 points. Well, of course, that means there's some group element, little gamma, that takes 1 point to the other. That group element conjugates the stabilizer group here to the stabilizer group there. And therefore, it gives you a map of the set of conjugacy classes here to the set of conjugacy classes there. That map is independent, it's a bijection, and it is independent of the choice of the group element. That's because a group acts on itself. Any finite group, let's say, acts on itself by inner automorphisms, but the resulting action on the set of conjugate classes is trivial. It is the trivial action. So it's well defined to talk about, in this sense, that we have these canonical bijections. It is well defined to talk about the set of conjugacy classes of the stabilizer group. It's independent of which point in the orbit that you pick. Now, so how do we actually do this? How do we carry out the construction? Instead of just collapsing each orbit to a point, replacing each orbit by the set of conjugacy classes of the isotropy group. Well, we form a space x tilde. It's the collection of all pairs, little gamma, little x, in gamma cross x, such that little gamma fixes little x. We look at all such pairs. And this, again, it's by definition, it's included in gamma cross x. This is, again, an affine variety. It's a subvariety of gamma cross x. But the original finite group gamma acts on this space x tilde. This is the formula for the action of gamma on x tilde. So given one of these pairs, little gamma, little x, and a group element g in gamma, we let g act, we conjugate the first. In the first variable, we conjugate by g, and in the second variable, we just apply the original action. And that then gives us an action of gamma on this space x tilde. And then what will be called the extended quotient, denoted in this way, x / gamma, is x tilde divided by gamma. In other words, the extended quotient, x tilde / gamma, is the ordinary quotient for the action of gamma on x tilde. Now, everything's been done here within the context of affine varieties, so the extended quotient, again, is an affine variety. Now, if we look at the projection, just the standard projection from gamma cross x to x, we restrict that to x tilde, so we then get a map, a projection map from x tilde to x. But the way the action of gamma on x tilde was defined, there it is, see, little gamma, little x just goes to x. The way the action on gamma on x tilde was defined in the second variable, it was just the original given action. Therefore, this is a gamma equivariant map from x tilde to x, and so it passes to quotient spaces. And so we have the projection of the extended quotient onto the ordinary quotient. But we also have an inclusion of the ordinary quotient in the extended quotient, because we have the identity element of E of gamma, the identity element E of gamma, and we can map any point in the variety to the pair E comma X. E certainly fixes X, so we are in X tilde. And this is a gamma equivariant map, and then we get an inclusion of the ordinary quotient in the extended quotient. So the extended quotient, in a canonical way, contains the ordinary quotient. So the extended quotient, you can always think of it like this, that you will have the ordinary quotient, will be in there, and then there'll be other stuff due to the fact that the action is not free. You'll have other things. You'll have your ordinary quotient sitting in there, and then you'll have other things due to the fact that the action is not free. If the action is free, you don't get any of this. You just get the extended quotient and the ordinary quotient are the same if and only if the action is free. The action of gamma on X is free. So this is called the extended quotient. Now, our p-adic group G, in the topology it received, we are working over p-adic field F. That field F in its it's a topological field. It's locally compact and totally disconnected. But G receives a topology from that, and in that topology, G is locally compact and totally disconnected. So we can fix a Haar measure, let's say left invariant, although these reductive groups, for the most part, in fact, are unimodular. But let's say we fix a left invariant Haar measure, and then we can form the Hecke algebra, which we will denote like this by HG. So this is the convolution algebra of all locally constant, compactly supported, complex value functions going from G to the complex numbers. The addition is completely naive. The addition is just naive pointwise addition. The addition is not using the group structure at all. What's interesting in this algebra is the multiplication, which is convolution, and as usual, it's given by this formula. So this is the Hecke algebra. And then a representation of the Hecke algebra, well, this is now pure algebra. It's just in the sense of ordinary algebra. This is just a homomorphism of algebras over the complex numbers, going from the Hecke algebra to the endomorphisms of some complex vector space. And that's what we mean by a representation of the Hecke algebra. And then we have the standard definition of irreducible. A representation of the Hecke algebra is irreducible. First of all, it should not be the zero representation. I mean, that's not considered to be irreducible. But, so it shouldn't be zero, and there should not exist a proper vector subspace which is preserved by the action of the Hecke algebra. That's what we mean by irreducible representation of the Hecke algebra. Our primitive ideal in the Hecke algebra, this is the null space of an irreducible representation. So a primitive ideal, that means we have the Hecke algebra. It's going by an irreducible representation to the endomorphisms of some complex vector space. And the primitive ideal is the null space, so that this is exact. Now, there is a canonical, this is an utterly canonical thing, bijection of sets from the set of primitive ideals in the Hecke algebra to what we are interested in, which is the smooth dual of the group. This is a completely canonical thing. If you have a smooth representation of the group, it integrates to give a representation of the Hecke algebra. And if you start with an irreducible representation of the smooth, irreducible representation of the group, you integrate it, you will get an irreducible representation of the Hecke algebra, and then you take the ideal. And this is a bijection. In fact, there's even you can make this categorical. There's an equivalence of categories between smooth representation of the group and non-degenerate, what are called non-degenerate representations of the Hecke algebra. But in particular, we have this bijection, this utterly canonical bijection. Now, has anything been gained from that? I mean, we want to describe we wish to describe the smooth dual. We want to study the smooth dual and hopefully prove local language. Have we gained anything by going to primitive ideals in the Hecke algebra? I mean, maybe maybe nothing has been gained, but actually something has been gained. Because on the Hecke algebra, we have a topology. On the set of primitive ideals in the Hecke algebra, we have a topology, the Jacobson topology, due to the algebraist, Nathan Jacobson. So any topology can be described by its closure operation. So if we have a completely arbitrary subset of the primitive ideals, so we have some set of primitive ideals, then the closure in the Jacobson topology, so you take your primitive, now primitive ideals tend to be big. They are often maximal. So you take this collection of these big ideals and you intersect it. You intersect them and you get a little tiny ideal. And then you take all the primitive ideals that contain that little tiny ideal. That's the closure operation in the Jacobson topology. So we have a topology. That's what's been gained. We have this Jacobson topology. And now the primitive ideal space, the set of primitive ideals, which is canonically identified with the smooth dual, you give it this Jacobson topology, it's then the disjoint union of its connected components. And this gives you what it means, connected components, a little bit of point set topology. You define what it means for a subset of a topological space to be connected, and then you say that two points of the topological space are in the same connected component if there's a connected subset and they are both in there. And so that the connected components are the maximal connected subsets. And for quite a while, actually, I had a mistake in this slide, a mathematical mistake. And none of the eminent and wonderful mathematicians listening to my audience and listening to the talk pointed that out. However, my undergraduates last semester did point it out. They did point it out. But this is correct. What's up there now is correct. So don't say you didn't learn anything in this talk. All right, now, that is correct, what's up there. All right, now, so in particular, we can take the primitive ideals with the Jacobson topology. It's going to be the disjoint union of its connected components. In fact, each connected component is both open and closed. And the connected components, these are known as the Bernstein components. These are the Bernstein components. I mean, we identify the primitive ideal space in the Hecke algebra with the smooth dual, and these are the Bernstein components. And then pi naught, that is the set of the connected components. This is a countable set. It has no further structure. It's just a discrete countable set. Now, what was Bernstein's view on this? So let's discuss how Bernstein looked at this. So this pi naught of the primitive ideals, this is known as the Bernstein spectrum. So Bernstein's point of view on this was as follows. You take what are called cuspidal pairs. A cuspidal pair, that consists of a Levy factor of a parabolic subgroup P of G. And sigma is an irreducible supercuspidal representation of M. So this has been a recurrent theme in many of the talks here. That is, you go down to Levy subgroups and take cuspidal objects. This recurred, I think, in many of the talks. And then you put an equivalence relation on the set of all these cuspidal pairs. The equivalence relation is the conjugation action of G combined with tensoring the irreducible supercuspidal of the Levy by unramified characters of M. Now, unramified means the character is trivial on every compact subgroup of M. And So these are the simplest sort of smooth characters you could possibly have. Here's a bit more on that. So in other words, two cuspidal pairs, m sigma and m prime sigma prime, they are decreed to be equivalent if and only if there exists an unramified character psi from m to the non-zero complex numbers and an element g of our p-adic group G, such that when you apply G to M and then you tensor sigma with the unramified character, you get M prime sigma prime. In other words, G conjugates M to M prime, and when you push forward sigma tensored with the unramified character psi, that is equivalent to sigma prime as smooth irreducible representations of the Levy group M prime. So this is the equivalence relation Bernstein puts on the set of all the cuspidal pairs. And it's then a fact that there's a canonical bijection between pi naught, that is the set of these Bernstein components, and the cuspidal pairs divided by this equivalence relation. So so this is Bernstein's point of view on this, that you are looking at this. This is your Bernstein spectrum. So if we have alpha in pi naught, then G alpha hat, this will be the corresponding connected component. So the problem of describing the smooth dual, it now breaks up into two problems. One is to describe the Bernstein spectrum, to describe this discrete set. That involves figuring out what are the irreducible supercuspidals of the Levy subgroups. And the second problem is, suppose we fix an alpha in pi naught. So we fix, let's say, a cuspidal pair. Describe the Bernstein component. What is the structure of the Bernstein component that we get? So the first problem, that's to determine the Bernstein spectrum. So you have to in some way figure out what are the irreducible supercuspidal representations of the Levy subgroups of G. And the basic conjecture there is that if you have a reductive p-adic group M, for example, M could be a Levy factor of a parabolic subgroup of G, then any irreducible supercuspidal representation of M is obtained by smooth induction from an irreducible representation of a subgroup of M, which is compact modulo the center of M. So you can pass down to these smaller subgroups, compact modulo center, and get any supercuspidal. And this has been verified now in many examples. Now, for the second problem, that is describing the structure of individual Bernstein components, so let's see what my coworkers and I propose about this. Well, C cross, as usual, will denote the complex affine variety, C with 0 removed. The coordinate algebra there is Laurent polynomials. So a complex torus is a complex affine variety T such that there exists some isomorphism of affine varieties from T to a finite Cartesian product of C crosses. It doesn't have to be canonical. It's just that there exists some isomorphism. We call that a complex torus. Now, it is part of Bernstein's theory that he assigns to each alpha in pi naught, he assigns a complex torus and a finite group acting on that complex torus. His complex torus, in fact, is a complex algebraic group. That is, there exists a non-negative integer r such that as an algebraic group defined over the complex numbers, this Bernstein's torus is non-canonically isomorphic to a finite product of C crosses. However, the action of Bernstein's finite group on this torus is not in general. Speaking generally, it is not in general as automorphisms of the algebraic group, but only as automorphisms of the underlying affine variety. in many examples, in the first examples that anybody studies, it is in fact acting as automorphisms of the algebraic group. But there are examples, there very definitely are examples, where it acts as what you might call affine transformations. That is, there's an automorphism, a typical element will act by an automorphism of the algebraic group, but then a translation. There are affine transformations in general. Well, Bernstein then forms the quotient variety and proves that there's a surjective map mapping this particular Bernstein component back to the quotient of his torus by his finite group. Now, this map plays quite an important role in all of this. This is called the infinitesimal character, or the central character, or the cuspidal support map. Now, this map is surjective, finite to 1, and generically 1 to 1. What I mean by generically 1 to 1 is that we have in here, we have, let's say, if this is the ordinary quotient, we have in here the subvariety. See, if this is, let's say, the ordinary quotient, we have in here the subvariety consisting of all the points in this ordinary quotient, all the points where the preimage has more than one point. And that's a subvariety. It's a proper subvariety. So if you remove this and remove its preimage, then what's left, it's 1 to 1. So that's what I mean by generically 1 to 1, that off a subvariety, it's 1 to 1. So this is the theory of Bernstein. And so if you have a cuspidal pair, then we can talk about the Weil group. So it's M sigma. We can talk about the Weil group of M. It's the normalizer within the p-adic group G. It's the normalizer of M divided by M. This was called, in these fascinating talks that we heard about the Springer correspondence, this was referred to as the relative Weil group, right? I think the word relative somehow sneaked in there. Well, I'm just, on this slide here, it just says the Weil group of M. Now, Bernstein's finite group will be a subgroup of this Weil group. Namely, you start with a cuspidal pair. You take all elements in this Weil group of M such that when you move the sigma by that element in the Weil group, all you get is sigma tensored with an unramified character of M. So it preserves sigma. It's the subgroup that preserves sigma up to tensoring by unramified characters. And then Bernstein's complex torus is a finite quotient of the complex torus consisting of all the unramified characters of M forms a complex torus. Bernstein passes to a finite quotient of that, and that's his torus. So this is his finite group, and this is his torus. So this is actually a very good situation. It's not exactly that you have, let's say, the maximal torus and the Weil group of the group acting on the maximal torus, but it's never too far from that. It's not that, but it's somehow not sort of wildly far away from that. Okay. Now, the way Bernstein constructs the Bernstein component is by doing parabolic induction. This has also been mentioned in many of the talks. You start with a cuspidal pair, M sigma. You allow yourself to tensor sigma by unramified characters. And then you do what has occurred in many of the talks. You do parabolic induction, smooth parabolic induction. That is, first you pass M up in a rather immediate way to the parabolic group, and then you do induction up to G. And then you take the distinct irreducible subquotients of that. That's how you produce this. And then this map back down here, the cuspidal support map, you basically are mapping you're mapping your point here back to the inducing data from which it came. That's essentially what this map is. Now, so in studying the representation theory of these groups, you wish to understand what these Bernstein components are and what this map. This map is an important part of the picture, the central character or infinitesimal character. You want to understand what that map is. All right, now the conjecture of, well, I like to call it the ABPS conjecture. So we have a connected split reductive pionic group. And we have fixed an element in pi naught, so we have the Bernstein component, and then we have Bernstein's map to the ordinary quotient. On the other hand, we could form, I mean, nobody can stop you from doing this, you can form the extended quotient. See, we are in a perfect context to form the extended quotient. And then we could take this naive projection from the extended quotient back to the ordinary quotient. So our conjecture is that there is a certain resemblance between these two things. And this concludes today's talk. No. What I would say is this, that if this were the good old days of Italian geometry, which of course was great mathematics, as everybody knows, if it were the good old days of Italian geometry, we could leave it go at this. But it's not the good old days of Italian geometry, so we have to try to be precise. So let's try to be precise. Now, of course, the point of this is this. Let me try to explain what the point is. The point is that this can be really quite difficult to calculate. I mean, this can be quite difficult to figure out what this is. But this is the real thing. This is what we are interested in. This, on the other hand, just about all the time, this is very easy to calculate. I believe that a computer could be easily programmed to do this. But I also believe, I don't know for sure, but I think that this is beyond what computers can do with present technology. So what I like to say is that this is real life. This is what we really want to understand. This is real life. And this here, this is something made up by mathematicians. That's the difference. Now, all right, here's a more precise form of the conjecture. These two things are almost the same. Well, of course, what does that mean? All right, so we're talking about connected split reductive pionic group, okay. And we have fixed one Bernstein component. Okay, so to be precise, the conjecture says that there exists a bijection. So we have fixed some alpha in pi naught. And we're saying that there exists a bijection between the extended quotient and the Bernstein component, a bijection with the following properties. Now, within the admissible dual, we have the tempered dual, the smooth tempered irreducible representations. And the set of that within the smooth dual is the support of the Plancherel measure. Within Bernstein's torus, we have the maximal compact subgroup. Now, despite the fact that, generally speaking, Bernstein's finite group is not acting as automorphisms of the algebraic group T sub alpha, nevertheless, the action does preserve the maximal compact subgroup. I mean, the translation part in the affine transformation is of finite order, because it's a finite group that's acting. And so that implies that it preserves the maximal compact subgroup of the torus. And so we can form this same extended quotient construction for the action of gamma sub Bernstein's finite group on the maximal compact subgroup of the torus. And so the first property of so that will give an orbifold. And so the first property of that the that this conjectured bijection is to have, the first property is that it will map this orbifold that we make sitting within the extended quotient to the tempered part of the Bernstein component. So that's the first part. So the tempered representations that are in that Bernstein component will appear as an orbifold within a compact orbifold within the extended quotient. The second property is that for many alpha, this diagram does not commute. So I would assume that you are saying, oh, well, that's bad, that's bad. Well, actually, it's neither good nor bad. Well, I think basically it's good, to tell you the truth. There is no way you can make it commute. That is absolutely impossible. And let me take a moment, but you will see that the non-commutativity of it is a basic part of this whole picture. The reason it does not commute is this. We have, let's say, one side of the, let's say, the easy side. So let's say we have the easy side. I mean, this thing that's very easy to calculate and figure out. And then we have the interesting side, the side that we really are interested in. So that's the Bernstein component, mapping by Bernstein's map to the quotient. Now, the reason that the diagram cannot commute is, you see here, in this picture, there will be a subvariety where the pre-image has more than one point. I call that the subvariety of non-isotypicality. Well, we need a good word for that. The point is that when you do the parabolic induction, these are the points where you get a representation which is not isotypical, which has distinct irreducible components. So this is, that really should be over here. You see, you have this subvariety of non-isotypicality. Here, I don't know. These are just the points here, which have more than one point in their pre-image. And this is the same thing. I mean, this is the subvariety of non-isotypicality. It's the set of points here where the pre-image you have more than one. Now, these two varieties are in the same algebraic variety. They are in this quotient. But they are not usually the same. They are not the same thing. Therefore, it is impossible for that diagram to commute. But it will do the next best thing. You see, the point is that even though these two subvarieties are not, generally speaking, of course in some examples they are the same, but generally speaking they're not the same, you can connect them by what's called a flat family. That is, you can deform you can move one to the other by what's called in algebraic geometry a flat family. So they are not the same, but they are as close to being the same as they possibly could be. Let's put it that way. Conjecturally, a lot of this is conjecture. Conjecturally, there's a flat family. We checked in, my coworkers and I, we checked it in many examples. We published a counter-undo note about this, on this point, that there is a flat family connecting these two subvarieties. Now, so we are continuing with the conjecture. In this possibly non-commutative diagram, the bijection going in this direction is continuous. where you use the natural topology. Here you are giving this the Jacobson topology as primitive ideals in the Hecke algebra. Here you are giving this affine variety the Zariski topology. And this composition is a morphism of affine algebraic varieties. So we now have two. We have two morphisms of affine algebraic varieties going around the diagram this way. They are not necessarily the same. They might not be the same. But they come as close to being the same as, I mean, this is all conjectures here. They come as close to being the same as they possibly could. Namely, there's what you might call an algebraic homotopy from one map to the other. That is, we have an algebraic family of morphisms of algebraic varieties parameterized by C cross. Theta 1, in this family, if you let T be 1, you get the easy thing. If you let T be the square root of Q, where Q is the order of the residue field of F, then you get the thing you are really interested in. See, then you get Bernstein's map. So the two maps are not the same, but they come. This is very unusual in algebraic geometry, that you can algebraically deform one map to another. Now, but it's a bit more than that. It's part of the conjecture that this deformation from one map to the other is achieved in a rather special way. It's achieved by using co-characters. That is, we're saying that for each irreducible component in the extended quotient, there is a co-character, that is a morphism of algebraic groups from C cross to Bernstein's torus, and you use that co-character to create this algebraic homotopy. You use this family of co-characters to create this algebraic homotopy. Well, these co-characters cannot come from out of the blue. Where, in examples, they actually come from the SL2C part of the Langlands parameters. I mean, when you study examples, you begin to see that this is where these co-characters are coming from. That is, you restrict your Langlands parameter. Langlands parameter is a map from the Weil group of F cross SL2C to the Langlands dual group of G. You restrict this to the maximal torus here, which is one-dimensional, and you get a co-character. And that's where these co-characters are coming from in the examples we studied. Now, I'd like to show you how all this works in a very simple example, which other speakers have also often decided to use. So GL2, F, and we will take what's called the Iwahori component, that is all the smooth irreducible representations having a non-zero Iwahori fixed vector. Now, so we have fixed this Bernstein component. Now, Bernstein's torus, in this case, is the unramified characters of the maximal torus of GL2F. And that's, in a canonical way, that identifies with C cross cross C cross. Bernstein's finite group, in this case, is the Weil group of this p-adic group. In other words, it's the two-element group, and it's acting by interchanging the two non-zero complex numbers. So when you form the extended quotient, what happens? Well, you will get the ordinary quotient, but then this action is not free. It has fixed points. I mean, you have a whole C cross of fixed points, namely everything of the form zeta comma zeta. So for the extended quotient, you'll get the ordinary quotient, and then you have this extra part, which is a C cross. That's the extended quotient in this example. But what's the real life situation? So here, this is supposed to be describing the easy situation. Now, the curly brackets means unordered pairs. See, this is the ordinary quotient. So it's unordered pairs of non-zero complex numbers. So in the easy situation, the locus of non-isotypicality, that is the points that have, so we're in the ordinary quotient, the points that have more than one point in the pre-image, it's unordered pairs zeta 1, zeta 2, such that zeta 1 equals zeta 2. But in real life, when you actually work out the representation theory, the locus of non-isotypicality, oh, it's called locus of reducibility here. Okay, all right. If you prefer, you can call it locus of reducibility. It's the points that have more than one point in the pre-image. Well, this locus actually depends on Q, that is on the order of the residue field. It's unordered pairs zeta 1, zeta 2, such that when you form the unordered pair zeta 1, zeta 2 inverse, zeta 2, zeta 1 inverse, you get the unordered pair Q, Q inverse. So you can see in this example that there's no way that the diagram could possibly commute, that these two loci are different. On the other hand, you see here you'll have 2 points in the pre-image, and the same actually is true here in the honest representation theory. Here you have 2 points in the pre-image. And the correcting co-character that you need here is given by t goes to t comma t inverse. On the part of the extended quotient that is just the ordinary quotient, the correcting co-character is always trivial. There's no correcting done there. So on the extra stuff, this is the correcting co-character in this example. This is what you correct by, and then you get a diagram that commutes. So this is supposed to illustrate what is going on. Here's the easy situation. You have the ordinary quotient. It just maps by the identity map to the ordinary quotient. Then you have this extra C cross, and that goes down to what you might call the diagonal C cross here, to unordered pairs zeta 1, zeta 2, such as zeta 1 equals zeta 2. Now, in the real life picture, the really interesting picture, again, there's no correcting being made on the extended quotient. That just goes by the identity map down to the ordinary quotient. But the extra part, this extra C cross, that maps to this locus that depends on Q. So this is the difference between the two pictures. There is a philosophical point here. Namely, I think you might agree that the easy picture is gotten by setting Q equal to 1. In other words, the easy picture is gotten by degenerating the order of the residue field to 1. Well, there is no such thing really as a field with one element, although Alain Kahn and his co-workers for quite a number of years now have been developing the theory of the field with one element. And so this actually connects at this point to what Alain Kahn and his school have been doing. There's a certain connection here. So the idea is that we are degenerating the order of the residue field to 1. We then get a very, very easy picture. But then it turns out that it's not all that difficult to figure out how to get back to the true picture. That's the philosophy that comes up here. Well, this suggests a method for proving local Langlands. Namely, you want to get from, let's say, a Bernstein component to that part of the Langlands parameters that should belong to that Bernstein component. You want to find a map. So if you have a bijection here, then all you have to do is somehow map the extended quotient to these Langlands parameters. Well, if you try to do it like this, if you follow word for word what's up on the screen here, it is my belief that you will get absolutely nowhere, because this geometric structure is not present in the Langlands parameters. So I think it is the case that you won't get any place. However, there is a very interesting construction due to, I think it began with Lustig. Vogin was involved in this, and I think other people, which is called enhancing the Langlands parameters. In Pramod's talks about the Springer correspondence, it's not enough to just have a unitary a unipotent class or a nilpotent class. You want to get a bijection to ear of the Weil group, you have to, he used the word enrich. You have to take pairs consisting of a unipotent class and a certain kind of irreducible representation of what he called the A group. Well, something very much, I'm sure that Lustig and Vogel and so on were inspired by what happened with the Springer correspondence, because you can enhance or enrich the Langlands parameters in much the same way. There is, so to speak, an A group. It acts on a variety of Borel subgroups in the Langlands dual. And then you want a certain sort of representation of that. And so you take pairs consisting of a Langlands parameter and the enhancing or enriching representation of the finite group. And the point of doing that is that then you will get then you expect to get a bijection here. So this geometric structure should appear in the enhanced Langlands parameters. So you have a method of attack here on the Langlands, local Langlands conjecture. You have to first establish, well, and then you see your map, the map you are looking for. I mean, the whole issue in local Langlands is to get the map. The map you are looking for will be that you take the inverse of this bijection and then you go here. And if you don't like, and then you can always project back to the Langlands parameters by forgetting about that little extra representation of the finite group. So you have a method here for approaching local Langlands. And so with my coworkers, for a split-connected reductive p-adic group, you have a Bernstein component in the principal series. The principal series, that means that the cuspidal pair, that the M, the levy that appears in the cuspidal pair, is the maximal p-adic torus of the p-adic group G. So we checked that if you have any Bernstein component in the principal series, then, well, we need a mild restriction on the residual. The residual characteristic of the p-adic field should not be too small. I believe that's not essential, but we needed that for the proof. In fact, Roger and I checked some cases where that is not satisfied, and it was okay. But anyway, we need this for the proof. And we then check that you do. You do, in fact, get this bijection. It has the properties involved that we were talking about. And then we had a go at local Langlands from this point of view. And what we found was that you can work on these two arrows by completely different methods. The methods you work on them are logically independent of each other. They're just totally different methods that you can use for each arrow. This one here is representation theory of affine Hecke algebras. Ideas of Lustig are what is called Lustig's asymptotic algebra are quite important here, are used here. And also beautiful results of my coworker Martin Soleveld are used for this arrow. Now this arrow is Springer correspondence. It's what we have been hearing about. However, it's not Springer correspondence for, as was in the main, for Weil groups of, let's say, connected reductive complex Lie groups. You have to extend this Springer correspondence to affine Weil groups. However, that is some interesting mathematics involved there, and it works out quite beautifully. My coworker Roger Plyman worked this out, and it was really quite beautiful what he did. But then, alas, there was a big disappointment. It was already in the literature. However, it was in an extremely obscure journal that I never heard of, and alas, there it was. So anyway, this turned out But believe me, this is Springer correspondence. Now, of course, as usual in these kind of things, I'm brushing various technical things under the rug, but I should say that local Langlands for Bernstein components in the principal series, this was first done for the Iwahori component by Kazdan and Lustig a long time ago. Then it was done, but they needed a hypothesis that the center of G is connected, of the p-adic group G is connected. That's a pretty restrictive hypothesis. And then Mark Reeder, he did it for any based on what Kazdan and Lustig did, he did it for any Bernstein component in the principal series. But he also needed that hypothesis, that the center of the p-adic group G is connected. And that, if you look at your usual suspects there, most of them do not satisfy that hypothesis. Anyway, we don't need it. We were able to, with technical work, and using this approach, we were able to do away with that hypothesis. Now, what about L packets? Now, suppose that local Langlands is true. Up until now, I've not been assuming that it was true, but suppose it happens to be true. So you get your correcting co-characters, these co-characters that allow you to construct this algebraic homotopy. So you have one correcting co-character for each irreducible component of the affine variety, the extended quotient. Now, there may be repetitions among the correcting co-characters. The correcting co-character for the ordinary quotient, which is one of these components, is the trivial co-character. It may happen that you get repetitions, and it's these repetitions that give rise to L packets. So in other words, we have a conjecture here that 2 points in the extended quotient are in the same L packet, if and only if the two correcting co-characters are the same. Well, there's there's a labeling. You have to label. Usually it's done by unipotent classes in the Langlands dual group. You make a labeling of the irreducible components of the extended quotient. They have to have the same label. And throughout the algebraic homotopy, these 2 points go to the same thing. Now, I want to comment about this a little bit. About what is being said here. Ed Frankel came to a talk I gave about this a while back, and he made a very interesting comment. You see, when we look at Bernstein's map, and it's been known for some time that, so this is Bernstein's map. It has been known for some time that the intersection of an L packet with, if we have an L packet, any L packet, we intersect it with this Bernstein component, it lies within one fiber of this map. This has been known for quite a while. So Ed Frankel's comment was this. He said, well, look, now we have a second map, which I keep saying is not the same. He said, easy. 2 points are in the same L packet, if and only if both maps take the same value on the point. Now, that was actually a very, very good guess by Ed Frankel, and you can think of it that way. What's up on the board is an elaboration of that. I mean, in other words, it's a bit. This is not quite the correct if and only if statement. What's up on the board is an elaboration of that. In other words, it's not just that the two maps must agree, but throughout the algebraic homotopy, on all those maps that occur in the algebraic homotopy, the 2 points have to have the same value. So, but then there's a little technical extra point about labeling, which is usually done by unipotent classes. Yeah. There's a word up there in red. Warning. An L packet. I gave a talk about all this in Jerusalem a while back in Kajdan's seminar. Bernstein was at the talk. And at this point, he looked very worried. I remember how worried he looked. He looked very worried about it. Is he here? Is Joseph here? I don't know. Is he? Okay. So you're off in Napa Valley drinking wine or something. All right. Now, in fact, my friend Peter Schneider, he came to the first talk I ever gave about all this, and he assured me after the talk that it was complete and total nonsense. Well, Peter is in Napa Valley drinking wine as we speak. Okay, now, so Joseph Bernstein looked upset in Jerusalem because he thought I was saying that this describes the L packets. It doesn't. It only gives a certain partial information on the L packets. So let me try to explain that. The point is that an L packet, and this came up, Joseph Bernstein suddenly looked relaxed and very pleased and very happy. All right, now, the reason that it just gives certain information. It doesn't describe the L packets because nothing says that an L packet has to lie completely within one Bernstein component. That is not true. An L packet can be spread out over several different Bernstein components. In fact, if you want to start getting involved, which you should, with the inner forms, that is, with the non-split forms that have the same Langlands dual group, then an L packet is actually it's not only in several different Bernstein components of the original group you started with, it also has points over in the smooth dual of the inner forms, in other groups, in other words. But so what this is doing is that you first fix a Bernstein component, and then this is conjecturally, these are conjectures, is describing the intersections of L packets with this fixed Bernstein component. That's what this is doing. Now, perhaps a more ambitious version of what we are doing here could, in the end, describe the L packets. That this, I don't know. I think it's conceivable, but I don't know. So I'd like to show you an example of this. So again, let's take a very simple example. So we have SL2F. And again, we will take the Iwahori component, that's one Bernstein component, the smooth irreducible representations having a non-zero Iwahori fixed vector. So the unramified characters, this is Bernstein's torus in this example. It's the unramified characters of the maximal torus, and that identifies with C cross. The Weil group is, in fact, Bernstein's finite group in this example, and it's the two-element group. But the way it's acting now is by a non-zero complex number zeta goes to zeta inverse. That's the action. Now there are two fixed points when you map zeta to zeta inverse, namely 1 and minus 1. And so for the extended quotient, you will get the ordinary quotient, where you divide out, you identify zeta with zeta inverse, you get the ordinary quotient, and then you get these two extra points because of the fixed points 1 and minus 1. So here is the picture. See, now the curly brackets denotes unordered pairs. So in the easy picture, we have the ordinary quotient. That maps by identity to the ordinary quotient. And we have these two extra points denoted by minus 1, and 1, 1. And they are just mapping down to themselves, you might say. But here it's very much like the other picture. See, here we get this maps down. This extra point here is mapping. This is in the real life picture, the actual representation theory. This extra point is mapping it down to minus 1, minus 1. And this extra point, there's a Q dependence, is mapping to Q, Q inverse. the unordered pair, QQ inverse. Now the correcting co-character here, which you need here, see, in order to correct this to get over to this, it's t goes to t squared. But here there is no correction, so you have a repetition. See, the correcting co-character here is trivial, and the correcting co-character there is trivial. So the conjecture predicts that you should have an L packet here. And in fact, that is what happens. So I hope this gives some idea of what is happening. So the extended quotient is conjecturally, it's a little bit non-canonical. I'll try to explain that a little bit. In bijection with the Bernstein component, and thus provides a setting in which precise bookkeeping can be done for L packets and correcting co-characters. Now, we have, of course, these fascinating and beautiful ideas of Langland's, the local Langland's conjecture. We have the conjecture that of this talk that was discussed here. There's a conjecture of Alencon and me, which is a K-theory conjecture. It's a K-theory statement. So it has some analysis in it, but also a certain kind of algebraic topology. On one side, it has to do with representation theory, and on the other side with geometry. And I like to say that the conjecture of Alencon and me is like a sort of a topological shadow of what's really happening. The conjecture of Alencon and me is for locally compact groups, but in particular, it's for pianic groups. So people used to ask me, well, what's the relationship to local Langlands? I couldn't answer the question, although my coworker Roger Plyman began to come up with answers. Well, finally, you see, we have this conjecture of today's talk, and that interacts with both, with the conjecture of Alencon and me and with local Langlands. So this kind of presents a link. My coworker Roger Plyman I like what Roger said about this. He said, if you take the conjecture of Alencon and me, it's for a locally compact group. It could be Lie groups, could be discrete groups. But let's do reductive pianic groups. Roger said, just the other day, here at Misery, Roger said, you take the conjecture of Alencon and me and you apply it to reductive pianic groups, then you strip away all the K theory and all this stuff, just strip all that away and see what the real structure is and what's really going on. And according to Roger, you arrive here. So I think this was kind of an interesting comment. Now, for Vincent Laforgue, you have to be a little bit careful. This is not Laurent Laforgue. This is his younger brother, Vincent Laforgue. He proved that the conjecture of Alain and me is valid for any reductive pianic group G. Then we have, of course, the amazing and beautiful work of Harris and Taylor, and also Guy and Ia, that local Langlands is valid for GL and F. And Roger and his co-worker, Jacek Brodsky, they proved that what we are talking about today, everything we've been saying today, this is valid for GL and F. So for GL and F, we have a very happy story. All the conjectures are true. On the other hand, as several speakers at this meeting have said, GL and F gives you a false sense of security, right? I mean, this has come up over and over. I mean, the L packets are singletons, and there's a lot that's very, very special about GL and F. Nevertheless, there it is. For GL and F, a happy, happy story. Thank you for your attention.